that you need to work with pressure. So when you are frequently have the time limit, when you have the stopwatch, you can minimize the pressure. All right. So let's start with the discussion assignment 3. I hope you have done, everyone. Okay. So this is the question. The water flow through a horizontal pipe as presented in figure 1. This is a flow rate. We call as a Q. The pipe consists of two sections, diameter 4 inch and 2 inch. This is the imperial unit with smooth reducing section. The pressure difference between two pipe section is measured by a mercury manometer, neglecting friction effect. Determine the differential height, which is the H of mercury between the two pipe system. So basically, when we analyze this question, all right, we can see what can we do. First, we can see we have the manometer section. When this is manometer section, we can use the pressure difference P2 minus P1 equal to negative rho G Z2 minus Z1. And then this is consists of the flow. We have the flow. That means we can use the Bernoulli equation. Can you see? We have two concepts that need to combine. Manometer and Bernoulli. Right? So, let's start with Bernoulli equation first. Alright? I want to investigate what is the value of H, right? What is my H? So, now apply the Bernoulli equation at point 1. For example, this is at point 1. Okay. And this is at point 2, just above the tube. And then this one at point 3. And this one, okay, at point 4. This level is same as point 3. Alright, so I want to start the Bernoulli equation at point 1 to point 2. So, how should I start? Okay. So, I start with P1 over gamma plus V1 squared over 2G plus okay, plus Z1 equal to P2 over gamma plus V2 squared over 2G plus Z2. This is Bernoulli equation. So we can see that at the different it is at the same level. Let's say our reference point now here. So this level with this level is the same. So we can cancel Z. So what's now? We can simplify the equation. So P2 minus P1 over gamma of water. We consider this is gamma of water equal to V1 minus V2 squared over 2G. And then I want to move this one to the other side. It will be P2 minus P1 equal to gamma. Gamma is specific weight, yeah. V1 minus V2 squared. over 2G. The gamma now I want to expand in terms of rho G. So it becomes rho of water gravity V1 minus V2 squared. Okay. Over with 2G. So gravity and gravity we can cancel out. We will get, okay, rho of water, velocity 1 squared minus velocity 2 squared over with 2. Let's say this is equation 1. Clear? So far until this part you clear, yeah? Any question? Any question, class? Clear, yeah?
Clear, Doctor.
Okay, thank you. So, you can see that I need the P2 minus P1. I need this one. Where should I get this one? After I use the Bernoulli equation at this one, where do you think I can get P2 minus P1? From which section? What do you think? From which section I should get P2 minus P1?
Two.
From?
Time two.
Can you speak louder?
Time meter.
From the manometer?
On the time meter. Time.
From the diameter?
Yeah.
Okay. You can get from the manometer. Alright, this one. So, now we are considering point 1 and point 2. I want to get my intention here. From manometer, I want to have the relationship of P2 minus P1. Now this is 4, this is 3. So I should extend further. I should calculate from this one. Okay, my calculation now start from 1, go to 3. 3 go to 4. 4 go to 2. Okay. So, here I start with from manometer reading P3 minus P1. Can you see this one? I want to go from 1 to 3. Please remember that pressure at 1 is different, yeah, with pressure at 3 because this is water. Okay. So P3 minus P1 equal to rho of water gravity Z3 minus Z1. So, rho of water, this is negative. Negative rho of water gravity. Z3, what is the value of Z3? And what is the value of Z1? Class? Do you know what is the value of Z3? Do you still remember? Pardon?
0.
0. Yes, perfect. How about Z1? How about Z1? Which one?
H plus 4. H plus 2.
Okay.
4.
You don't know maybe you don't know this height, right? From here to here. So let's say this is X. Okay. So Z1 basically, okay, let's put Z3 equal to 0. Minus bracket Z1. What is Z1? Which is X plus H, right? Z3 equal to 0. Okay. Z4 equal to H. Z2 equal to Z2 equal to what? Same lah. Right. So from here, this is our reference. So Z3 minus Z1, which is Z1 X plus H. Okay, and then from 3 go to 4. So this 3, we jump, it is the same. 3 go to 4. So P4 minus P3 equal to negative row of mercury now, Hg. Z4 minus Z3, negative row of mercury. So Z4 is H minus Z3 is 0. And then from 4 go to 2. So P2 minus P4 equal to negative row of water. Now we are dealing with water. This is water, yeah. Z2 minus Z4. Negative row of water, gravity. Z2 is X plus H minus Z4, which is H. Okay, Z4 is H. Alright. So from here, negative row of water, gravity. Negative row of water, gravity. This is positive lah, yeah. Positive water, gravity, X. Okay, positive, negative, row of water, gravity, H. I expand only, very simple. So this is row of negative row of water, mercury, gravity, H. Alright, and then this is negative row of water, gravity, X, minus row of water, gravity, H. Okay, basically no need lah, this is cancel. Okay. So, from here, you can cancel out P3. You can plus lah everything. Plus, plus, plus. You can cancel P3, P3, P4, P4. Now, you get P2 minus P1. P2 minus P1 equal to this one, yeah? This one. This can cancel this. Alright. Yeah, alright. Okay, let's double check. Okay. Negative, 0, minus, plus. Okay, good. Alright. Okay. Okay, okay, now I understand. Okay. So, this one calculation wrong. Okay, this is positive. Alright. Because this is multiplication. Multiplication. Alright. Now it become negative, negative, positive. Alright. So rho of water, gravity H minus rho of mercury, gravity H. So P2 minus P1 equal to H, rho of water, Hg, rho of water minus rho of mercury. Okay, now we have equation 2. So equate equation 1 and equation 2 together. One and two. So equation 1 is this one. Density of water V1 squared minus V2 squared over 2 equal to this one. Hg, rho of water minus rho of mercury. Okay. So from here, I need to calculate the velocity. Okay, I can see I can get the velocity. You know that from the volume flow rate, Q equal to A multiplied with velocity. So to get the velocity equal to Q over A1. Q over A2. So I want to get, okay, find velocity 1 and velocity 2 from Q. So Q is 1 gallon per second, which is 1 gallon per second. So V1 equal to Q over A1, right? So 1 gallon per second divide with area. Area here, when you look at here, it is circular. So using pi r or pi d squared over 4. So pi over 4 multiply with diameter. Diameter is 4 inch. I need to convert into foot. So 4 divided with 12. Okay, square it because this is diameter. And then you need to multiply 1 gallon. 1 gallon of water is equivalent to 0.13368 feet cube. So cancel out gallon, and then you solve it, you will get the answer is 1.53 feet per second. And V2 the same, Q over A2, which is 1 gallon per second divided with area. Area is 2 inch. I convert into feet. 2 divided with 12, square root multiply with 1 gallon of water equal to 0.13364 feet cube. You will have 6.13 feet per second. So, and then it is given that the density of water, okay, the density of water basically is 62.4. And then the density of mercury, it is 847. You can look at the table. Okay, make sure you use the you use the imperial unit. All right, just substitute into, let's say this is equation 3. Equation 3. Okay. So Okay, so from this one, rho of water V1 squared over V2 squared over 2 equal to H gravity, rho of water minus rho of mercury. In order for us to clearly to substitute, better we make the H become the subject. Okay. Rho of water sorry. Rho of mercury. So I simplify further this one. I move bottom, it become division. V1 squared minus V2 squared over 2GH 1 minus rho of mercury over rho of water. Now I can simply substitute. Velocity 1, I get 1.53 squared minus velocity 2, 6.13 squared. Divide with 2. Gravity should be 32.2, yeah. And then 1 minus density of mercury is 847. Density of water 62.4. You will get negative 35.236 divided with negative 0809.747. So the final answer would be 0.0435 feet. So I want to convert back into inch. Just multiply with 1 feet 12 inch. I will get 0.522 inch. Okay, any question so far?
Doctor,
Class? Yes.
the gallon here is UK or US?
It is UK. It is basically it is it is another unit lah, such as centimeter, meter, kilometer. Okay. So sometimes we use gallon because it depends on different location. For example, it is involved of oil and gas. You have the gallon of gas, a gallon of oil. You can use the gallon. Okay, you can. This is the unit conversion lah. Gallon is equivalent to 0.13368 feet cubic feet. Okay, any question? Clear, yeah? On how to get the H? Class?
Yes, doctor.
Okay, now we proceed to the question 3. A siphon water pump as shown in figure 3 is used to pump the water from a large reservoir to the lower tank that is initially emptied. Water leaves the tank through an orifice. Determine the height h the water will rise in the tank at equilibrium and assume V1, V2 equal to V4. Let's say this is at this point, this is P2, this is P4. Okay. You can see this is pressure at 1 is equal to P atm. This is also equivalent to P atm as well. Alright. And the hint given is V2 equal to V4. So we should find V2 first. And then we should find V4. After that, equate V2 equal to V4. Okay. Apply. We have 1, 2, 3, and 4 points. Now let's apply Bernoulli equation. Okay, apply Bernoulli equation at point 1 and point 2. Okay, point 1 here and point 2. So, P1 over gamma plus V1 squared over 2G plus Z1 equal to P2 over gamma plus V2 squared over 2G plus Z2. Alright. Since P1 is exposed to the atmospheric pressure and it is nothing said about absolute or the gauge, we can consider PATM equal to 0. So our calculation now in the gauge pressure. Velocity. Okay. At this point, the velocity increase is very small, approaching 0. Because this is reservoir. Alright, it is hard to see the increments of velocity. So velocity 1 equal to 0. Pressure 1 equal to 0. And Z2, you can see. Now let's consider Z2 as our, okay, Z2 is our reference point. Okay. So Z2 equal to 0. So now what we have is we have okay, okay, we have a Z1 equal to P2 over rho plus V2 squared over 2G. Okay, you notice that the pressure at 2. Maybe this is at location lah, close to the tank. Okay. In order to get pressure at 2, you remember our equation rho G H. So this is the height multiply with the density of water and gravity, you will get pressure 2. Substitute in here. So rho G height over density of water. Okay, plus V2 squared over 2G. Okay, so the density of water, this one, I want to expand in terms of rho G. So I can simplify rho G and rho G. I will have Z1 equal to H plus V2 squared over 2G. Right, so it is given that V2 equal to V4. I need to find V2 first. So I rearrange. V2 become, okay, this one move to the other side. So Z1 minus H bracket multiply with 2G and square root. Okay, this is equation 1. After that, I will need to find V4. So I can use the correlation 3 to 4. Okay, apply Bernoulli equation at point 3 and 4. Okay, so again, write down the equation. P3 over gamma plus V3 squared over 2G plus Z3 equal to P4 over gamma plus V4 squared over 2G plus Z4. Okay. You can see that, okay, Z4 is also nearly at the reference line. Okay, so we can cancel Z4. Okay, because Z4 at the reference line. And then Z3. Where is the Z3? The Z3 from here to 3 is H. So Z3 is equal to H. And then P3 is equal to 0. Because this is a gauge pressure. Alright, and then V3. Okay, we can see this is the water tank. Alright, the velocity is very small, the increment. Okay, velocity at 3 is reaching 0, hardly to see. Okay, maybe this is the water tank, it's hardly to see. There is no change of velocity. So V3 equal to 0. P4. Okay, P4 is exposed to the atmospheric pressure. You can see PATM. So P4 equal to PATM equal to 0. Equal to 0. So cancel P4 equal to 0. What do we have? We have H equal to P4 squared over 2G. So rearrange V4 equal to 2GH square root. This is equation 2. Equate equation 1 and equation 2. 1 and 2. V2 equal to V4, which is square root of 2G Z1 minus H equal to square root 2GH. So power root both sides, you will get 2G Z1 minus H 2GH. Then you can cancel out 2G and 2G, you will have Z1 equal to 2H. So H basically Z1 over 2. This is equation 4. Alright. So, do you know what is Z1, class? This is Z1. From reference line to the top. So just substitute 15 feet per 12 per 2, you will get 7.5 feet. Okay, that's it. Any question? Us?
Doctor,
Yes?
why at the point 4 the P is equal to PATM?
Which one?
Point 4.
P which one? P4?
Yeah, P4, why is equal to PATM?
Okay, you can see here, a siphon water pump as shown in figure 3 is used to pump the water from large reservoir. Okay. The water leave the tank through an orifice. Okay, the water leave the tank through orifice. This is orifice lah. Okay, that means it pump. The water pump go inside through orifice. Okay, to the lower tank that is initially empty. Water leave the tank through an orifice. This is orifice lah. So through the orifice, it is exposed to the atmospheric pressure. So for example, this is nozzle. The water leaving here, maybe this is 0.1 and 0.2. The water at here is P atm equal to 0 because anything exposed to atmosphere equal to 0.
Oh, okay, doctor.
Okay. Any question? Do you understand, class, how it works?
Yes, doctor.
Okay, excellent. All right. I think let's proceed on the lecture. Okay. I want to finish until this one. Example. We do example this one, eh? Okay. This is Renault transport theorem. I hope you studied. All right. We go to example 2. The pipe flow fill the cylinder tank. Okay, that means there is a water flow from left to right at the same time fill up. From here, it will increase the water flow. Okay. At time t equal to 0, water depth in the tank is 30. Okay. At t equal to 0, you must understand it. T equal to 0, the water depth in the tank initially at 30. This is H. Centimeter. Estimate the time required to fill the rest of the tank. All right. So we need the time taken from H increase until full. So this is the diameter lah given. So now we can apply the conservation of mass where the control volume enclose the tank of the pipe. Okay. Okay, now we apply the conservation of mass for the water flow, which is, recall back, this is the change of control volume, rho dV. Okay, rho dV is a mass. Okay, the change of mass in control volume with respect to time plus control surface. Rho velocity average dot end product must be normal dA equal to 0. Apply the conservation of mass. Of mass. Alright. So from here, you can see that, okay, I want to consider my control volume as in the tank, cylinder tank. Okay. Control volume is fixed here. It will not change at all. Okay. Maybe like this. Okay, I consider. Alright. So what will be the change? Of course, this will keep changing control volume. My volume of water increasing from this one up until this one at the top. So from here, I write again d over dt. Okay, sorry. D over dt. Okay, from the control volume, I know that the volume is, the density is fixed because this is water, constant. So density is, this is incompressible. Multiply with area, multiply with height. Area, this is the area. If you look at here, the area will be circular shape. Multiply with the height. This is the volume. Plus, alright, plus this one, integration of control surface rho. Okay, you can see velocity. Velocity from here, we start from here. Velocity 1, which is, this is given, yeah, don't worry. It is 2.5. Okay, 2.5. Okay. In order for you to understand easily, it is better like this lah, I teach you. Okay, into the control volume, it is negative. Remember? Okay, into the flow into control volume, negative. Flow out control volume, it is positive. For example, this is control volume. Out of control volume, positive. Inside the control volume, negative. So now the flow is perpendicular to the control volume and it is into the control volume. That means it is negative. Okay, negative rho 2.5 dA. Okay, and then the next one is out of control volume, which is plus control surface rho 1.9. You can see this is V2. Okay, V2. And parallel to the end. Okay. This is dA equal to 0. So from here, okay, I can simply rho A dH over dt. Why? Because rho and A is constant. Okay, this constant I move outside. The change is only H. H keep changing. Okay, increasing. So that is why dH over dt minus 2.5. Okay, 2.5 rho of water area. When you look at this area, pipe area, it's circular. Okay, that means pi r squared. It is given that the radius. Okay, it is given the diameter is 12 centimeter. Use the radius. Multiply with 0.06 squared. Okay, plus 1.9 rho. Again, pi multiply with 0.06 squared equal to 0. So after you solve this one, okay, density of water 998, or you can put 1000. It's okay, don't worry. Area is a pi. Area of what? Area of this one. Okay, because this is referred to control volume. Control volume refer to this one. The top one, yeah. So the area is pi r, which is the radius, 75 centimeter convert into radius. So divide by 2. 0.7. This is centimeter, yeah, 0.75 divide by 2, square it, dH over dt equal to, minus with 2.5998, okay, pi 0.06 squared plus, substitute only, 1.9998 pi 0.06 squared equal to 0. So now what we have is dH over dt equal to 0.0153 meter per second. So in order to get the time to fill up the tank, okay, which is the tank initially 1 meter. The total is, H total is 1 meter. It's already filled with H initial is 0.3 meter because it is filled with this one, 30 centimeter. So, what is balance? H balance shall be 1 minus 0.3. It is equal to 0.7 meter balance. So that balance, I need to find the time taken. So this substitute to the balance, which is 0.7 meter. 0.7 meter divide with dt equal to 0.0153. So dt now become 0.7 divided with 0.0153. You will get 45.57 seconds. That's it. Okay. Do you have any question? Okay, class. That is how to solve the question. I just want to recap. The first, recap back the conservation of mass in terms of control volume. We have the change of control volume plus control surface. From control volume, you need to analyze which location the change happened inside the control volume. So I realize the change is here. So I focus on this as a CV. And control surface, I realize that it is appear at this surface. And then you can focus. This is control surface and this is control volume. And then you need to know which is a constant and which is vary. So density, you expand density is constant. Volume will vary because the volume of control, the volume of water inside the control volume will vary. So in order to get volume, area multiply with H. So you realize that the H will vary. So density and A outside and only dH over dt. And this is control surface. How to remember? Into the control surface is negative, out of control surface is positive. So put negative, rho velocity perpendicular to the area 2.5 plus with the velocity out of the control volume density 1.9, density multiply with volume, velocity 2, 1.9 multiply with the cross-sectional area. After that, substitute the value of density, water. Okay, I think this density you can remove lah because it is the same density. You can simplify further lah. Alright, and then you will get the rate dH over dt. The value is 0.0153. So the question quite tricky. Ask you estimate the time required to fill the rest. This is the question. The rest is the balance. So H balance is 0.7 meter. So just substitute 0.7 meter into the rate change of H. You will get dt, which is 45.6 seconds. Okay, any question, class? Is it clear? Is it clear now? Do you understand the concept? How to solve? Okay, this is your homework. Okay. I think that's all for today. You can do this one. Is quite easy. Same. Okay. I think that's all for today. If you have any question, please let me know. I end my session with Assalamualaikum warahmatullahi wabarakatuh.
Doctor, can I have the attendance?
Okay.
Thank you, Doctor.
Okay, welcome.
Thank you, doctor.
Thank you, Doctor.